Okay, Assalamualaikum warahmatullah and a very good evening. It's been a while. So today we will be talking about the earth leakage circuit breaker, residual current devices, earth leakage relay, and also earth fault relays. So I'll be touching a little bit on earth leakage and earth fault. How are the earth leakages or earth faults detected? Either through ELCB or RCD, or through earth leakage relay or earth fault relay, or other methods. And we'll be going through some comparison summary with regards to the ELCB, ELR, and also EFR. So what's an earth leakage and earth fault? So an earth leakage is basically a current flowing to earth due to an insulation fault. Meaning there's a phase to ground fault, a single phase to ground fault, a double phase to ground fault, or three phase to ground fault. Due to an insulation fault, there's an insulation failure. Then earth leakage current is basically the current flowing from the live parts to the earth, or extraneous conductive parts in the absence of an insulation fault. It's not really a fault yet, but there's some leakages current flowing through the from the live parts to the earth. So the differences are basically earth fault protection is intended to protect the equipment when there's an insulation failure. For instance, when there's a direct contact between the live conductor and earth. So under that condition, there will be a large or great fault current that will flow back to the transformer through its neutral point where it's connected to the earth. However, for the earth leakage current or earth leakage protection, the faulty currents are generally much lower, and the protection is dedicated, for example, to avoid hazards to human beings or animals. In magnitudes of milliamps as compared to the large earth fault, it will be in amps or up to kiloamps. So how are they detected? So we have the most basic that you can find at home is the earth leakage circuit breaker. Well, people normally call ELCBs for those voltage operated type, which is normally not used anymore in these modern times. What we will normally find at home is the current operated ELCB, or the residual current device, or the residual current circuit breaker. So that's the first type. That's the first method. Second is we can detect earth faults through earth leakage relay, and also some earth leakages, because the setting can be as low as 30 milliamp for earth leakage relay. For the larger earth faults, of course, it's an earth fault relay that we can find in the overcurrent earth fault or the OSEF relay. And there's also other earth fault detection methods, which we will touch briefly later. So what's a residual current device? It's basically it's a current operated circuit breaker. So it's normally referred for current operated ELCB, earth leakage circuit breaker. So the operating principle is quite simple. All circuit conductors, supply and return, are run through a sensing coil. So any imbalance of the currents will induce a large enough current to trigger the tripping coil. So if you can see here, this is a single phase ELCB RCD. So we have two live and neutral, supply in and return. So and there's a toroid here which will measure the current. So if there's any imbalance, means when the supply and the return current doesn't sum up to zero, it will induce within the toroid and will trigger the tripping coil. Same goes for the 3-phase 4-wire ELCB. So in this case, the toroid will be measuring all the 4 phases. So just a note, sometimes people will use this 3-phase 4-wire, 3-phase ELCB for a single phase. So please note where you want to connect the single phase, because not all the push button are connected. For the test push button are not connected on the same terminals. Some are connected on the 5th and 7th terminal. Some ELCB brands, they connect the test push button at the terminals 1 and the 7th. So you have to be careful, because sometimes you already connect to single phase loads with a 3-phase ELCB, but it will not trigger any tripping when you press the push button, because you may have incorrectly connected. So the typical setting for this kind of ELCB that you can find in the market is from 10 milliamp, 30 milliamp, 100 milliamp, 300 milliamp, and up to 500 milliamp. And there are some which is as large as 1000 milliamp. And it's considered as instantaneous time, which is about 40 millisecond. Okay, so this is the typical technical data of any ELCB that you will find. The RCD. Sorry for my bad. Supposed to call it RCD. So we have 2 poles, 4 poles, normally up to 63 amps. The current rating up to 500 milliamp. Okay. So normally only used for low voltage. Up to in here it's only up to 400 volts. Alright. So now we go to the older version of the earth leakage circuit breaker, which is the voltage operated type. So if you can see here, this is the model. Looks just like a normal breaker, but it's actually an ELCB which is operated by voltage. So why do they say it's operated by voltage? We'll go through. So ELCB, normally when you say ELCB, it refers to the voltage operated type. If it's current type, we will call it as RCD or the residual current device. So the principle of operation is quite simple. We have one terminal here connected to the ground, which is to your electrode, your ground electrode, or your grounding. Where else the F terminal is connected to the frame. F is for the frame, metal frame. So whichever metal frame that you have in your house, in your buildings, so all the metal frames must be connected to this F terminal. So you will be look around if there's more than one metal. So this is normally normally at your switchboard there'll be the earth terminal. So all the metal frames of your sub DBs or any other downstream metal parts will be connected to this F terminal through looping or bonding of other earth conductors. So under normal operation, the voltage across E and F is negligible, or would say almost zero. So when there is a fault, for example, when there's a live to ground fault or neutral to ground fault, live to ground fault, so there will be a voltage rise across VEF, voltage across EF. So normally it will rise up to the line voltage. So this line voltage will trigger the tripping. So it operates based on the voltage built up across the E and F terminals. So normally the trip coil operating voltage is set at 50 volts. So why? Because 50 volts is typically the maximum or the largest voltage that is safe for a person to touch. Okay, so that's why we set it at 50 volts. However, why is it not used anymore during these modern times? So your earning electrode must be reasonably low impedance, maybe 100 ohms, 300 ohms, 500 ohms. For example, if you want to limit the person touching from a current of, for example, you want to limit up to 10 milliamp, 100 milliamp. So the grounding around here must be at least be 50 volts. 50 volts divided by 10 milliamps would be 50 divided by 0.1, 100 milliamps. So your grounding resistance must be at most 500 ohms or below. So any leakage more than 100 milliamps will trigger this the voltage coil. So your earth electrode must have reasonably low impedance. So people don't really check in the practical world, especially at homes, and also if you have very dry soils, the resistance will go up higher. So when there's a leakage somewhere, it may not be able to detect because the voltage across this E and F is not big enough to trigger the trip coil. Second is earth electrode must be positioned so that its resistance area does not overlap that of other electrodes. So because the overlapping resistance may cause nuisance tripping. Because when you're at home or you have a lot of residences, each house will have this kind of protection, and each house will normally have its own earthing electrodes. But due to earth itself becoming a conductor, so when there's an overlapping earth electrodes or earth resistance, so there's a fault in another building, may trigger nuisance tripping of the ELCB in the adjacent building. So, and finally, the most critical part is that if somebody touches the live part directly and he's stepping on the ground, this ELCB will never detect that because the current leakage is going directly from the live to the ground through that person. So in order for ELCB to be able to operate, the current must be able to travel back to the metal, then return back to the F terminal and go back to earth. So if somebody has a direct contact to any live parts, he's a sure goner because the ELCB is not going to help him. Alright, so that's why it's not being used basically. It's not really safe. And of course the setting is quite simple, 50 volts because of the maximum voltage that is safe for a person to touch, 50 volts AC, and it's instantaneous. Okay, so if you can see here, there's a yellow button here which is the push button. So basically when you test the push button, you are shorting from live to ground through some resistor. So that resistor, the build up is already limited to 50 volts, just enough to trigger the ELCB. Third is the earth leakage relay. So we have the earth leakage relay. This is most common use, especially for industry. So we have here the monitoring, the relays itself, and also the sensor. Okay, so it consists of two parts. One is the monitoring relays, and another part is the sensor. So here we have the type of sensor which is a core balance CT, core balance current transformer, which it becomes the input to the earth leakage relay. So this earth leakage relay will trigger the tripping through the shunt trip or something like that, or directly through an under voltage shunt trip coil, under voltage trip coil. So the principle is quite simple. It consists of an earth leakage relay and a ZCT or CBCT. ZCT is basically a zero sequence current transformer. So how it works is very simple. So under normal condition, if you see here, we have 4 wires, 3-phase 4 wires. All 4 wires are coming in. 3 phases are going out, and the return for single phases load through the neutral. So under normal condition, the summation of all these 4 currents will be 0. So the magnetic flux produced from all the 4 currents are 0. Let's say there's a fault somewhere in one of the phase. So the magnetic flux produced by the summation of all these 4 currents will not be 0 anymore, and it will be induced within the core balance CT or the zero current, the zero sequence current transformer or the ZCT. So if the current is large enough, which is flowing the secondary of the ZCT, it will trigger the tripping coil of the earth leakage relay. Alright, as you can see here, we have 4 wire CT. So red, yellow, blue and neutral. So it has to go, all the 4 wires must go through the ZCT or the CBCT. Where else if this is not a neutral wire, which is the earthing wire, so the earth wire should not pass through the ZCT, because sometimes there might be nuisance fault somewhere, and faults will just return back to the transformer through earthing. So that earthing, it can travel through this earthing cable. So if you put this earthing cable within the ZCT, so that the return earth fault current from somewhere else may trigger nuisance tripping of the ELR due to the ZCT or the core balance CT reading it. So trip setting, as far that I have come to see is Schneider and some other brands. They have from 0.03 or 30. Sorry, this is a typo. It's supposed to be 30 milliamps. From 30 milliamps up to 30 amps. So it depends on the brand. So it is some are adjustable, some are not. So the trip time is also adjustable from instantaneous up to 4.5 seconds. So this is based on the Schneider brand. Okay. Let me correct that for a while. 30 milliamp. Alright. So where were we? So special note. ZCT of different brands will have different turns ratio. People are not really aware that ZCT have some turns ratio just like a normal CT. So it is not advisable to match ZCT and ELR of different brands. For example, you want to use a ZCT from Schneider and match it with a ELR from Terasaki. No, never do that because the ratio is different. I will show you on the next slide. So the accuracy will not be correct lah. Maybe oversensitive, maybe less sensitive. Alright. So that's why it's always advisable if you want to use ZCT, you must ELR, you must use the same ZCT from the same manufacturer. Unless you know that the ZCT of the different manufacturers are having the same turns ratio, then it should be no problem for you to interchange with any ELR. So some of the common installation mistakes is that earth wire are passed through the ZCT, like this. In this case, earth wire should not pass through, but some people they just pass through. So especially must be really careful, especially when doing high voltage termination, cable termination for a 3-core. You must remember that the screen wire and the earthing wire from that termination must not pass through the core balance CT. The second most common installation mistake is that people always think that when it's used for neutral wire with 3-phase or 4-wire system, so the neutral wire is normally not passed through the ZCT or core balance CT. For example, if you see in this case, this neutral wire is actually being laid outside. So if this is only used for a 3-phase load, no problem. But if inside your 3-phase 4-wire loads, downstream there is a single-phase load, and if the single-phase load is large enough, it will trigger because the summation will not be zero because of the neutral. There's a neutral current returning from the single-phase load. Alright. So this is one example from Terasaki. This is quite old. I think 30, 40 years ago it's already there since the late 80s or 90s. So we have here the sensitivity. You can adjust from 30 milliamps up to 1000 milliamps. The operating time also is also adjustable from 0.04 or I would say instantaneous 40 milliseconds up to 2 seconds. But here it doesn't mention what is the turns ratio of the ZCT. But you must use the same brand for ELR, for Terasaki from ZCT and the ELR. So here's another example from Schneider, ELR from Schneider Vigirex. I think it's quite common in the industry nowadays. So just one note here. Sorry. So we have the fault is adjustable. Detection is adjustable from 30 milliamps up to 30 amps. You can also set some alarms, and the time also is adjustable from 0 to 4.5 seconds. Okay, just want to to have you a little bit focused on here. So here is given the ZCT or the combined CT is given. The transformation ratio is given, which is 1000/1 or 1/1000. So actually there's a ratio. Like Terasaki, we do not know what's the ratio for that ZCT. So if you were to use the Terasaki ZCT with this Vigirex, it may make it less sensitive or oversensitive. Okay, so that's why I say that you must use the same ZXT and ELR of the same make or same brand. And number 4 is the earth fault relay. So this is the normal earth fault relay that we find in the overcurrent fault scheme. So here we have three wire system. I assume this is high voltage. So we have 3 CTs here, red, yellow and blue, going through 2 relays on the red and blue phase for overcurrent. And there's a earth fault relay. So if you can see here, this is the point. This is the common point for all the 3 phases of the secondary wiring of the CTs for red, yellow and blue. So by Kirchhoff law, under normal condition, when there's no earth fault, the summation of red, yellow and blue is 0. However, when there's one earth fault on one of the phases, there'll be a spill current or the leakage current. So when the leakage current will flow through this earth fault relay, and if big enough, will trigger the earth fault. So normally a fault relay, of course, it consists of the fault relay on its own, or a fault relay in an OSEF relay . So this is a multi-function relay . Okay, so the one shown here is a fault relay on its own. And also it needs a sensor which comes from the CT, core balance current transformer. So in this case, this is what we call as the residual connection type . So it will have 3 CTs. So if you are using this for a 3-phase 4-wire, must have 4 CTs, which includes the neutral CT. Then we can also use core balance current transformer, just 1 CT covering all the 3 wires, and the single input going directly into the earth fault relay. And of course, another one is the neutral CTs, which is the single CT located at the neutral to earth connection of a LV secondary of any transformer. Okay. So operating principle is quite simple. CBCT I will not mention. Residual connection, as I mentioned earlier. Neutral connection is when there's an fault. So any fault, it will return back to the transformer as the source, so that transformer neutral CT will be able to detect. So if it's large enough, the current will trip the coil of the ELR. So trip setting, this is typical setting, which is about 10 to 20% of the loads or the MDs, maximum demands full load current. Normally, if this is connected for use at the transformer, so you will take the full load current of that transformer, and you take about 10 to 20% of that value of that full load current. Then time delay depends. You can set it instantaneous or definite time with some definite time delay, or using an inverse definite mean time, like the normal inverse curve or the very inverse curve or the extreme inverse curve under ANSI or IEC. So again, just to highlight what is the common installation mistakes that people do, because people always look at the high voltage side, they only remember 3 wires only. So when they use it on the 3-phase 4-wire system, they tend to forget about the neutral CT, because you must remember that for low voltage, we also have single phase loads, and there will be a normal neutral current return from these single phase loads. So if you do not have that neutral CT, the summation at the common point of all the 4 CTs, all the 3 CTs will not be 0. And then sometimes earth wire pass through the covalent CT, similar to the covalent CT that was mentioned earlier. Okay, so this is an example of a fault relay. This is brand Mikro. I think it's made in Thailand or in Malaysia. So we have a fault relay. So there's a lot of models for this brand Mikro. So there are some that comes only with the definite time only, instantaneous only, and also that the NX232A, which comes with everything . You have the definite time from instantaneous to set delay, and also those with the IDM pickles. Okay. What else here? So the input is one. In this case, it only uses 5 MCT lah. So some relays they can accept 1 M and 5 M. Some relays you have to really check lah. 1 M or 5 M only. Some relays you can change the jumper internal of the relay to set it as 1 M or 5 M lah. So you have to really know when you specify lah, your protection. So what are other methods that are available? We only mention here only because it will take some time to do that. I have a video on that, so please go through on that. So we have the frame leakage arranged for detecting earth faults online, and also circulating current differential protection, or normally we call it as REF 64 or 87N, and also ground fault neutral displacement of voltage. This one doesn't use current detection, it uses the zero sequence voltage transformer. So it's basically a normal, it uses a voltage transformer. Primary side is, if I'm not mistaken, is also star connected, and the secondary side is an open delta. So under normal condition, the open delta, when the voltage are balanced, when there's no fault, the voltage are balanced, so the open delta output will be 0 volts. But when there's one of the phase shorted to ground, so the open delta voltage will increase to some value lah. So you may go to this link. Please look at this video. I'll leave a link in the description. Okay, let's go back to our presentation. Okay, pretty much that's the typical methods that are used for fault detection. So if you can see here, I've put in a summary of table the differences and the commonality between ELCB, voltage operated type, residual current device, ELR, earth leakage relay, and also earth fault relay, EFR. So ELCB is a voltage detection, the rest are all current detection. Residual current is small, milliamps, earth leakage current from milliamps up to large currents, 30 amps, and also earth fault relay lah, up to 1000 of amps lah. In the low voltage, maybe kiloamps. So the trip setting is 50 volt AC for the ELCB, then low leakage current up to 500 milliamps for the RCD, and the ELR up to 30 amps. Fault relay up to 10 to 20% of the full load current. And the trip time, as mentioned earlier, you can go through. Just to note, just to highlight to you guys, because I'm talking this from a Malaysian electrical regulations perspective. So ELCB is pretty much not allowed. It's not even mentioned in any of the wiring guideline by the local authority here. As you remembered earlier, it doesn't detect any faults when there's a direct contact for a human. Okay. For the RCD, the regulations mention some settings, maximum settings. For example, 10 milliamps for wet or public area. For example, if you're using this for a water heater at home, you must have a 10 milliamp residual current device. Then for equipment that is possibly touched by hand, metal part, electrical equipment, metal part which possibly touched by hand must be protected by 30 milliamp. Anything other than that is 100 milliamps. For the regulations, it doesn't mention about earth leakage relay, but maybe used similar to RCD tripping lah, because it can be set as low as 30 milliamps. So in these ranges are still applicable lah. So earth fault relay doesn't mention anything lah under this regulation. The important part is that it must have a earth fault protection. That is what the electrical regulations say lah. So in terms of protection, for the ELCB and the RCD, it's mainly protecting human protection. And to some extent, it can be used also as a fire protection. So this is based on NFPA. So it states that anything 300 milliamp and below can be used as a fire protection. So if this is going to be used, for example, I take from this IEC 60364, you can see on the note below. At a high fire risk location, you can install this 300 milliamp maximum ELCB or RCD. Sorry, 300 milliamp maximum RCD or ELR to protect any fire risk locations. For earth leakage relay, it depends because the ranges is from 30 milliamp up to 30 amp. So for the low leakage current up to 300 milliamps is for human protection and fire protection, and the rest basically for equipment protection. For earth fault relay, mainly is for equipment protection. Human protection, not really lah, but it will still trip lah when somebody touches any live part. And finally, the typical loads being used with earth fault protection, just example. So water heater, 10 milliamp, domestic distribution board, lighting power distribution board, motor starters, low voltage. For the ELR, for feeders, motor starters, incomers are also used, but the setting is up to 30 amps. So for example, if in your standard or your specification you say that your motor starters only allow maximum setting of 10%, so the maximum load for motor starter using ELR will be 300 amps. So that is coming about to maybe close to 200 kilowatt, about 180, 190 kilowatt. Where else for the earth fault relay is mainly used for the distribution side up to the high voltage 33 kV. For the grid, normally earth fault is not really being used. They use some other kind of protection because maybe it's hard for them to discriminate. But for TMB, most of the grid transmission line, the fault disabled. They use other kind of protection, differential and also distance protection. Okay. So if you think this material is good, please share this material to your electrical friends, and do subscribe to my YouTube channel, Crux of EE, and then my Facebook page. Please like my Facebook page, facebook.com/Crux of EE. And if you have any other questions, please throw them in the comments below, or you can email me directly at cruxofee@gmail.com. Thank you.